In this video, I want to prove the following famous mathematical series, in particular that they evaluate to these values. And I want to do it in a simple fashion without calculating convoluted integrals or complicated integrals. I just want to do it starting from the function sine of x divided by x. In particular, this function, when you analyze it, it is quite easy to see that it has zeros, and the only zeros are located at x equal to n pi, where n can be any integer belonging to z, excluding n equal to 0. So n equal to 0 is excluded. So n can be equal to -1 or -2, -3, and so on, but it can also be equal to the positive version of these integers, 1, 2, 3, and so on. 0 is excluded, because if you set x equal to 0, or you take the limit, we know that this function evaluates to, the limit as x goes to 0 gives you 1. So that's not a 0 of this function. But apart from that, the sine of x has zeros at x equal to n pi, where n is a non-zero integer. Now, since we know the zeros, where the zeros are located, we know that this function can also be expressed as a product of terms of the following kind. So here I'm putting these dots, and let me tell you what I mean by this. And then here I have a term of this kind, 1 minus x divided by minus 2 pi, and here I have 1 minus x divided by minus 1 times pi. Then here I have 1 minus x divided by 1 times pi. And then I have 1 minus x divided by 2 pi, dot, dot, dot. So as you can see here, I'm simply writing these functions, which are linear in x, and I'm multiplying them out. You can see that each single term contained inside these parentheses becomes 0 exactly at one of the zeros of the function there, because, for example, this is 0 when x is equal to minus 2 pi, which is one of the zeros when n is equal to minus 2. And similarly here, when x is equal to minus 1 pi, we get a 0, and then at x equal to 1 pi, and here at x equal to 2 pi, and so on. So the dots represent the fact that here you have an infinite number of terms. For example, you have 1 minus x divided by minus 3 pi, and so on. And similarly here you have 1 minus x divided by 3 pi, and so on. I have written these terms like this, 1 minus something, because we know that as we let x go to 0, the product should give rise to 1. So since we set x equal to 0, here you just get 1. And 1 multiplies 1, 1, 1, and so on. You have an infinite number of 1s, but of course the multiplication will give you 1. So in principle, you would have to write, when you have a function, a polynomial, in general, you have all the zeros of the polynomial, and you write the polynomial as x minus the first 0, x1, then you have x minus the second 0, x2, and so on. And here at the front, you have a multiplicative constant that depends on what kind of polynomial you are considering. In this case, it is very, very similar. We know all the zeros of the function, therefore the function must be written in this form. In principle, there could be a constant here, a, but we know that the constant should be equal to 1, because when we set x equal to 0, the result of these products should give us 1. Now, another way to write a series, because if you multiply all these products, well, you understand easily that you will get a series of terms that depend on x squared. You also have the initial term, which is just 1, and so on. But you can obtain a series also if you expand the sign of x. We know that the sine of x is equal to x minus x cubed over 3 factorial plus x to the 5 divided by 5 factorial, and so on. So you have an infinite number of terms, and in principle, so this is a Taylor series that holds true when x is very close to 0, but according to complex calculus, you can write down an expansion for the sign exactly in the same way for whatever value of x you choose. Now, if you multiply all these terms, in particular, we can multiply the terms in the following fashion first. We can multiply this with this. So when we multiply these two together, so you have 2 pi and minus 2 pi here. So it's easy to see that you have minus 1 minus x squared divided by 2 squared pi squared, right? And similarly, when you multiply these two, you get 1 minus x squared divided by, well, you have pi squared here. Simple as that. Therefore, you see that you can write sine of x over x like this, divided by x, so you have 1 minus x squared over 3 factorial, plus x to the fourth over 5 factorial, plus dot dot dot. But you can also write the same thing in the following fashion. 1 minus x squared over pi squared, 1 minus x squared over 2 squared pi squared, and so on. So you have 1 minus x squared divided by 3 squared pi squared, dot dot dot. Now, out of all these terms, you can think that when you multiply all the ones that are contained in this expression, you're going to get 1, which is the first order term, and that will cancel this one. Then you will get one of these terms. So, for example, let's assume that all the terms that are contained, let's assume that all the parentheses, so this is the first parenthesis, this is the second parenthesis or second term, whatever you want to call it, and then so on, all the way up to infinity. But let's assume that we have n, capital N of those terms, and we know that n goes to infinity, but just think that at first this is finite. You choose one of these terms, and then you're going to, let's assume that you multiply this term with all the ones, all these ones, and how many do we have? We have n minus 1 of those, right? And you can do so for each of these terms. So the term that's going to multiply x squared is the following. So this is equal to, we get 1 minus 1 over pi squared, and then you get 1 plus 1 over 2 squared, plus 1 over 3 squared, plus 1 over 4 squared, plus dot dot dot, and you have an infinite number of them. And, well, this is exactly the summation over n from 1 to infinity, 1 over n squared, right? So this summation here would have to be equal, in particular, 1 over pi squared, times this summation, 1 over n squared. This should be equal to 1 over 3 factorial, which is 1 over 6. So what we get from here is exactly the first summation that we wanted to prove, this result here. And how do we prove the next one? And in principle, there could be others that you can prove, but the next one comes from considering two of these terms multiplied together in such a way that you're going to get x to the fourth, and then, well, you have to multiply with all the other ones, which are n minus 2. And how can we write that? Well, we know that we get something like this. We get some constant c, which multiplies x to the fourth, and then you have higher order terms. So the constant c will have to be equal to the following. In particular, we have to sum over n greater than m, and then we have 1 over pi to the fourth n squared m squared. And why do we get this? Well, we can choose, for example, this term which multiplies this one. Here you have, of course, a factor 1 over pi to the fourth, and you also have x to the fourth. And then you have 1 over 1 squared, which multiplies 1 over 2 squared, right? and you have already considered these two. Then, of course, you can multiply this 1, so you get a 1 squared. You multiply it with the next one, and it would get multiplied by 1 over 3 squared, and so on. So you can multiply 1 squared with all the other terms. So you get a series of the kind 1 over 1 squared times 1 over 3 squared, like this, plus dot dot dot. So you cannot multiply this term with itself. And similarly, if you choose this one, well, you have already multiplied it with this one in the previous consideration that we made. So what you can multiply it with is the subsequent term, which is 3 squared. So you get 1 over 2 squared, and then the first term is 1 over 3 squared here. Then you can multiply it with the subsequent one, so it's 1 over 2 squared, and then you get 1 over 4 squared plus dot dot dot. And now you should get the idea. Once you choose 1 over 3 squared, well, since you have already multiplied it with the first terms, with these first terms, you can multiply it with 1 over 4 squared, and so on. So the result that you get is basically this one. The constant c should be equal to this summation here. So basically you have to sum over n and over m, but in such a way that n is greater than m. Or if you want, you could also, this series here is the same as summation over m greater than n, or 1 over pi to the fourth n squared m squared. It's easy to see because of symmetry. It's very simple. And another thing that you can write is the following. This summation, due to the symmetry of n and m, can also be written as 1/2, and then you sum over n and over m, and you have, of course, this 1 over pi to the fourth n squared m squared, but you also have to subtract 1/2 summation over n equal to m, because if you remember, in these two summations, n is not equal to m, right? N should be greater than m, or if you want, you can also perform the summation in this way, with m being greater than n. And this is how you can write the summation, but in this way, it's simpler to rewrite, for example, this one. So you have minus 1/2. You can factor out pi to the fourth. This summation here, without the pi to the fourth, is simply equal to summation over n, 1 over n squared, and you square it. It's very easy to realize it, because n is just the dummy index. So when you multiply these two, since you are going to square it, you have a sum over n and the sum over m. So the summation is simply equal to sum over n, and then you also have a sum over m. And after that, here we subtract 1 over 2 pi to the fourth, and this summation can simply be written as summation over n, and of course here n goes from 1 to infinity, and you have 1 over n to the fourth. But now we can see that since this is equal to c should be equal to, if you check, the next term is just 1 over 5 factorial. So basically here this should be equal to 1 over 5 factorial. Since we know that this summation here is equal to pi squared over 6, well, we get an equation for this sum. And if you solve the equation for the sum, that's easy to solve. It is just algebra. What you get is that this is equal to 1 over 90 times pi to the fourth.